In this lecture, I'm going to talk about thermodynamic activities, which is section 5F in our textbook. And the purpose of an activity is to quantify how much a solution deviates from being an ideal solution. And I'm going to do this twice, once for solvent and once for solute. Because in the ideal case, we expect the solvent to obey Raoult's law, whereas in the ideal case for a solute, we expect it to obey Henry's law. So I need to do solvent and solute separately. All right, so in section A, we talked about an ideal solvent and its chemical potential. So a solvent, ideal solvent means a solvent in an ideal solution. Its chemical potential is its chemical potential as a pure substance plus RT, natural log, of the partial pressure of the solvent. And moreover, for ideal solutions, they obey Raoult's law. Which is that PA equals XA over PA star, which I can solve for XA for PA over PA star. Divide PA star over, I get XA. And now I can take that and put it up here. And so I get this formula, which we saw in section 5A, for the chemical potential of a solvent in an ideal solution. Okay, so that's for an ideal solution. Now we want to talk about a non-ideal solution. So let's talk about a real solution. And in the case of a real solution, what we do is we replace XA with what you can think of as an effective mole fraction. So XA is the mole fraction. We're going to replace it with an effective mole fraction, implying that the solution's behaving as if this were the mole fraction, even though it's not the exact one. And so we're going to replace XA with an effective mole fraction that we're going to call the activity. Okay, so for the activity of the solvent, we have A sub capital A. And making that substitution up here into our ideal solution formula, we get the formula for a real solution. And this is called the activity. Okay. Now, an ideal solution is a special case of a real solution. So in the ideal case, I can equate these two equations that are in boxes here. This one is, if you like, you can think of this one as it's always true, whether it's ideal or not. This one is true when it's ideal. So in the ideal case, these are both true. And so we're going to equate them. Okay, so equating the two equations in the boxes, we get this, where on the left here, we have the real solution. And on the right, we have the ideal solution. And in the case of an ideal solution, these two things must be equal because an ideal solution is still a special case of a real solution. So this is still true. And looking at this, it's straightforward to see that the activity is equal to PA over PA star. And this is a straightforward thing to measure in the lab. All right, now we've talked about this in the past, But Raoult's law is best obeyed by dilute solutions. And that's discussed on page 86 in my lecture notes. And so this means that as the activity approaches XA, sorry, there shouldn't be an as here. This is the activity approaches the ideal case, which is the mole fraction. Remember, the activity was replacing the mole fraction, where this was for the ideal case, this is for the real case. So as this approaches the mole fraction, or it does approach the mole fraction, as our solution gets more dilute. Okay, so as it gets more dilute, that means that XA is approaching 1, where 1 is pure solvent. Okay, now we can define a new quantity called the activity coefficient, which is defined like this. So the activity coefficient basically encapsulates the deviations from ideal. And so using this, it must be true, if we want this behavior up here, it must be true that the activity coefficient has to approach 1 as XA approaches 1, because as XA approaches 1, we expect A to approach X, and therefore gamma becomes 1 if A is equal to X. So gamma A has to approach 1 as the mole fraction approaches 1. And this is so that A approaches XA as XA approaches 1. So we're going to sub this formula for AA into the formula that we had for mu A. And so mu A then is mu A star plus RT ln, and it was the natural log of the activity, which we're going to replace with this. And since this is the ln of a product, then we can make this the sum of the logs. And I'm going to write them in this order. Because we recognize this part right here. So this is for an ideal solution. And then this piece right here represents the deviation from ideal. Okay, that's all I'm going to say about the activity of the solvent for now. Now let's talk about the activity of the solute. Okay, we were just talking about the solvent, and recall that we also discussed in section 5A, which this is on page 87 of my notes, that if the solution is ideal and dilute, then the solvent obeys Raoult's law, which is what we were just working with, whereas the solute obeys Henry's law. So now that we're talking about the solute, we're going to use Henry's law. Henry's law says that the partial pressure of the solute is proportional to the mole fraction of the solute, and this constant of proportionality is called Henry's constant. And Henry found this formula experimentally. So this K, this Henry's constant, is it's an empirical constant. And in fact, you calculated the Henry's constant on your last quiz. So that was quiz 5, question 8. You calculated Henry's constant. And it's also on page 88 of my lecture notes. So for a solute in an ideal solution, the formula looks just like it did for the solvent, the formula for the chemical potential, except now I'm using subscript B instead of subscript A. Remember, the convention is that A is the solvent and B is the solute. Otherwise, the equation looks the same. Sorry, this shouldn't be XB. That's only true for if it's following Raoult's law. This is the solute. It's going to be following Henry's law. So let me back up a step and call this PB over PB star. Which, remember, if this solute were obeying Raoult's law, PB over PB star would be XB. But we're not making that assumption. We're going to assume that this solute obeys Henry's law. And this equation I just wrote on the previous page, we're going to use this. We're going to substitute this up here for PB. So I get this. And I'm going to rearrange this natural log a little bit. I'm going to keep the KB and the PB star together, but I'm going to separate out the XB because it's a product with these others. So I can write it as another logarithm that's added to the first. Okay, and everything in these two terms is a property of the solute. This is always the same value. This and this are always the same values for the solvent or for the solute. So other than this temperature here, all of these things are basically constants. Okay, so these are all empirical constants, except T, still a variable. But we're going to call this the standard chemical potential, of this solute. Okay, so this is just a label that we're putting on this quantity right here. Okay, so this is the definition then of UB standard. You can think of it as this is how we define a standard state. Standard states can be defined however we want. And so this can be taken as the definition of the standard state for this solute in solution. And notice if this substance B also obeys Raoult's law. Raoult's law tells us that the mole fraction is equal to this ratio of partial pressures. And so now we're talking about something that obeys both Raoult's law and Henry's law, in which case we can take this formula for X, put it up here, and you see that the PBs will cancel, and I can solve this for PB star, and it equals KB. And if that's true, then this is the natural log of 1. And so in this case, mu B standard is just mu B of the pure substance. Okay, I've got a couple of equations that I'm going to combine here. First of all, let me label this one star up here at the top. And let me label this one down here star star. So first I'm going to solve star star here for mu B pure. So mu B pure is equal to mu B standard minus RT ln Henry's constant over partial pressure when pure. And now I'm going to substitute this into star for mu B star here. So this is going to go up there into equation that I called star. Okay, and I get this. So this right here used to be mu B star up in the top equation, and I used this to substitute for it. So this is mu B star plus RT ln the ratio of the partial pressures in mixture and pure. And now I'm going to combine these two natural logs. They both have coefficient RT in front. This one's negative. So when I subtract this one from this one, that's like taking the arguments and dividing them. So it'll be this argument divided by this argument. And when I do that, you see the PB stars cancel because they're both in the denominator. And I end up with PB over KB. All right, and we end up with this equation. And now the next step is, let's talk about a non-ideal solute. And we're going to do the same thing as we did with solvents. Okay, so as for solvents, we're going to replace the mole fraction with the activity. Where now I'm doing this for the solute. Okay, and when we do that, we get this equation. And if we compare this equation to the one in the box, then we can see that AB, the activity, must equal, oops, there should be an ln here, must equal this argument, right? Because everything else is the same, all right? So this gives us a formula for the activity of the solute. And as before, I'm going to introduce the activity coefficient. Which we call gamma B. And gamma B is the coefficient such that AB equals gamma B XB. So as before, this coefficient is encapsulating the non-ideal behavior. All right, so now let's investigate what happens to this activity coefficient, gamma B, in the case of a dilute solution. So a dilute solution is one where XB, the mole fraction of the solute, is very small, so as it approaches 0. Then we expect the solution to obey Henry's law as it gets more dilute. And one more time, I'll write Henry's law as a reminder. It's that the partial pressure is proportional to the mole fraction, and the constant of proportionality is called Henry's constant. So if this solution obeys Henry's law, what's the activity of the solute? So we already found the formula for the activity, PB over KB. But if this is obeying Henry's law, then we have a formula for PB. It's KB times XB. And the KB's cancel, and we're left with XB. So this is the ideal scenario, as expected. We replaced X with A, and in the ideal scenario, A should return to being X. Otherwise, A is the deviation from ideal. And so as XB approaches 0, then AB should approach XB. So what's the behavior of the activity coefficient in this case? Well, if AB is approaching XB, then this gamma B must be approaching 1 in order for AB to approach XB. So that will happen if gamma B approaches 1. Okay, so in conclusion, as XB, as the mole fraction of the solute approaches 0 as it gets more dilute, as it approaches 0, gamma B approaches 1. And compare this, let's compare this to the solvent case. So here's the case for solute. Here's the case for solvent. Gamma A approaches 1 as XA approaches 1. Here, it approaches 1 as XB approaches 0. Okay, so that's a fundamental difference between the behavior of the activity coefficients for solutes and solvents. Okay, now let's do an example of calculating the activities and calculating the activity coefficients. So we're going to return to this mixture that we looked at in 5A, which is a mixture of chloroform, which I'm going to use the letter C, and acetone. So and that'll be letter A. And I'm going to do this for two cases. One where the chloroform is the solvent, and one where the chloroform is the solute. Okay, so first let's do that C is the solvent. So if C is the solvent, we look back at our formula for the activity of a solvent, and it was the partial pressure of the solvent in mixture over the partial pressure in pure form. And this partial pressure here in pure form is something that can be measured and recorded in a table, and we can look it up. So that's given for chloroform to be 36.4 kilopascals. Okay, so now we need some data. So let's use the experimental data that I'm going to write down here. It's given in your book. Okay, so here's our experimental data. There's actually one more row. It gives us the partial pressures of acetone as well. But I'm just going to focus on chloroform. The acetone part could be a homework assignment. So let me pick one data point to start with. Let's pick this point where XC. So we'll start with the mole fraction of chloroform being 0.2, 20%. All right, now I can use this formula for the activity. And it's going to be this experimentally measured value, PC, which was 4.7 kilopascals, divided by PC star, which is 36.4 kilopascals, which comes out to 0.13. That's the activity at this mole fraction. And then we're going to do the same with XC equals 0.4, 0.6, and so on. We do the same thing with all the other mole fractions. And what we'll get is we'll get the activity as a function of the mole fraction. Okay, so I'm going to show you what that looks like in a minute. But before I do that, let's calculate the activity coefficient now. So if I start with the definition of the activity coefficient, and then what I'm going to do is I'm going to solve this equation for the activity coefficient. And so it's AC over XC. And okay, let's choose a data point. So now let's again start with 0.2 as our mole fraction. Then gamma C is going to be AC, which we just calculated for this data point, divided by XC, which is the mole fraction. And that's 0.13 times 5, so that comes out to be 0.65 for the activity coefficient. And then again, we're going to do the same thing with the other points. Okay, now let's do the case where C, chloroform, is the solute. So we look back in our notes and we see that the activity for the solute is the partial pressure of the solute over Henry's constant. And in this case, we already found Henry's constant in back in section 5A. So we found that Henry's constant for chloroform is about 23.5 kilopascals. You can see that calculation on page 88 of these lecture notes. Okay, so let's use the data now. And for the case for the chloroform, we'll do 0.2 again. Then AC is PC, which was 4.7 when the mole fraction was 0.2, divided by Henry's constant, which we found earlier, 23.5. And this comes out to be 0.2 exactly. All right, and we repeat for the other data points. And now we're going to find the activity coefficient. And we start with the definition, again, of the activity coefficient. Solve that for gamma. I guess you could take either of these as the definition of the activity coefficient. And so again, returning to the data, for the 20% case, gamma is going to be AC, which we just found right here was 0.2, divided by XC, which was the mole fraction of this data point, which is 0.2. So gamma C is 1. And then we repeat this for all the other data points. Once we've done that, now we have both the activity and the activity coefficient as a function of the mole fraction. So let me tabulate that data, all those results now. Okay, so here's all the data tabulated. All of the values of the activity and the activity coefficient, both when chloroform is the solute and when chloroform was the solvent. We can plot these. They're plotted in your textbook if you'd like to see them. But we can see the trends here that I want to point out. So in the case of the solute, we expected gamma to approach 1 as x approaches 0. And we see that is true, that gamma was getting closer and closer and eventually was exactly 1 as xc was approaching 0. So gamma c approached 1 as xc approached 0, which is what we were expecting. For the solvent case, we were expecting gamma c to approach 1 as xc approached 1. And we see that that was the case as well. Gamma c is approaching 1 as xc is approaching 1, which is what we expected for the case of solvent. Okay, and that's all I'm going to say about activities. Now we can start using those when we start talking about chemical equilibrium in the next chapter.